So students, today I will take this case of inductance. Inductance क्या है? It is a property to store magnetic energy by the virtue of opposition to the magnetic flux change. Magnetic flux change को oppose करने की tendency में there is always some stored magnetic energy, and that property is being used here. It is same and similar to the capacitor is doing electrostatics for storing electrostatic energy. Here it does for magnetic energy. Even the inductance also depends on geometrical parameters, means its length, width, size, and all the geometrical medium like that. It is there. So on the geometrical size and parameters, it depends. What we relate here? Simply the flux and current. Flux and current. With that, we get some. If we differentiate the flux function, we will get the current, and we can relate this function of inductance. Correct. So you have seen so many choke coils in the instrument used. They are called as inductors basically. In tube lights earlier it was used. तो choke coil जो instruments होते हैं, they are basically inductors. And here opposition to the flux chain, that is the basic property. So let us see this inductance. Inductance, correct. So it is what? It is property. It is the property to store magnetic energy. Magnetic energy. Property to store magnetic energy by opposing the flux change, magnetic flux change, by opposing the flux change in it. Correct. By opposing the flux change in it, we get this inductance. Okay. The solenoid is also called as inductor. Solenoid या toroid, these instruments or any current carrying instrument with certain geometrical parameters, we will see this inductance. And if I relate the inductance with magnetic flux, the phi is written as L into I, where this L is called inductance. This is your inductance. Meaning that what I will say, inductance L, if I say it is phi, the magnetic flux upon current, the ratio. Correct. Flux upon current, that define the property of inductance. Okay. That is one of the method to define this. Unit of inductance. Unit is Henry. Henry is the standard unit of inductance that we have. Correct. Now, if we have to find the this inductance for any geometrical size and parameter, that also we will see. Other way also we can find out this inductance E. It is minus d phi by dt. I write it is minus d phi by dt, and that value if I write, it is minus L into di by dt. This also I can say. So what I will say from here, the inductance L is equal to EMF over di by dt. So from here I will say inductance is equal to EMF induced if di by dt in the instrument is 1 ampere per second. This thing I can say. So these are the two methods I can relate them. This is the first one for inductance phi by I, and second one is this L is equal to this term, I can say E over di by dt. So these two equations, they will define the value of inductance. Any of the two will be mentioned and we can get the result. It plays the quite similar role at that of capacitor in electrostatics. Correct. Now, if I have to see this inductance in certain instrument like solenoid, I will see this inductance of solenoid. This value can see. Inductance, it is basically of two types. One is self inductance, other is mutual inductance. One is self, other is mutual. Self means the instrument itself opposes the flux change. Like once you do the switch on and off action of any electrical switchboard switches, अपने fan या tubelight, anything you are putting in on and off mode, there is always some spark because there is sudden current change. If current is changing with the solenoid instrument, if you see, the field will change, flux will change, that opposition will happen, and there will be some eddy current and spark happening. On off condition of switches, we always get this the spark is happening and there is a opposition to the flux change. So there are two types. One is self inductance with the symbol L and mutual inductance with the symbol M. Correct. So first of all, I'll see this inductance in the solenoid here. So what I say, suppose it is a solenoid arrangement here. ऐसे आप देख लेंगे. Correct. It is solenoid and it has the length L. Total length of solenoid is L. Current flowing is I here. And if I say area of one loop of solenoid is A, area of one loop of solenoid is A. So flux associated with this phi, I will say first of all the magnetic field B, B is mu naught N into I. This magnetic field with area of one of the loop is A, total number of loop is N into L. So this value will get mu naught N square AL into I, that is I, phi. This thing we have. Now if I relate the term self inductance L, you see it is phi over I. If I get this value here, so what you will get? It is mu naught N square A into L. All these terms are geometrical parameters and number of turns A and L. Na? So this self inductance you see, depending on the number of turns are getting closer, inductance will increase, area of each of the loop and length of the solenoid. Correct. This property, if you see the result what we have got, it is depending only on geometrical parameter. It depends. They are geometrical parameters only. You can see these are the geometrical parameters. So they are being used here for the solenoid. Correct. This thing I have. Area of cross section, length, number of turns, mu naught is the magnetic permeability of medium. Suppose sometime what I do, I put a soft iron rod across it. Okay. If I put a soft iron rod across it, say I have put it like this. If soft iron rod is put across here, the mu will change. So this I can see here the self inductance L dash, that will be mu times N square A into L. This value we can make. Correct. ये सारे results हम लोग यहाँ पे बना सकते हैं. Okay. So what I am saying, the new L dash will be mu naught times N square A into L. Sorry, it is becoming the mu, meaning that L dash is mu times N square A into L. This result we have. The medium also creates a chain. I am putting the iron rod. This is the iron rod, soft iron rod placed across the axis of solenoid. So this thing we have. Correct. So one of the method for defining this self inductance. Next, this self inductance can also be defined other cases also. Suppose I say this is a current carrying wire infinite long I, in the vicinity of it this is square loop. Now if I change the current here in this, the associated field and flux will change here. I can also find out the flux change and opposition for here also in the square loop. See, the square loop is of side length A, the side length is A, okay, and it is in the vicinity, and this length one side is also at a distance A. Now for this arrangement I can find out the self inductance, meaning that if current is changing here, some induced current will happen. So total this instrument can define the self inductance. How do I see? So first of all I need to find the flux associated with the loop. What I will get? If I have to get the flux, initially I will have to take the magnetic field with this loop, square loop, and field is changing with time, with x. I say this is x and the extension is dx. So small area here dA, you will say it is A into dx if it is a square loop. Now d phi flux, with this if I relate, what I will write, mu naught over 2 pi I by x, the field value due to infinite long wire, into small area this A into dx. If I integrate this function, I will get the flux, and coefficient of current here in the flux equation, that will define the self inductance. If I see this phi, you just see what is happening here, mu naught over 2 pi, just see I into A, this term, integration of dx by x, this thing I can write. Further I will say this phi value is mu naught over 2 pi I into A, integration of dx by x is ln x, this thing I can write. Now you see the value of A is varying from 1A to 2A. Integration I will change, put it from A to 2A, correct, A to 2A. So phi value, it is mu naught over 2 pi I into A ln 2A minus ln A, ln 2A by A, it is ln 2. This value is ln 2. So phi, again I write, it is mu naught over 2 pi I into A ln 2 I have. Now phi by I, that will be self inductance, it is mu naught over 2 pi into A into ln 2. You see all the terms here, they are the geometrical parameter. For this I have defined the inductance. The inductance for any arrangement we can see, and we can get. Here it was simple square loop in the magnetic field arrangement of infinite long wire, and I got this value result here as such, correct. The flux can be defined, and coefficient of current in the expression of flux will be the inductance. Here I can say this as self inductance and it will be Henry. Okay, this thing we have done. Now next, these inductances, once it is being found, we also have their series and parallel combination. Some inductance, suppose here if I have to see inductance for two inductors in series, they say this one and this another inductor, they are attached to some varying current. Suppose I am putting some AC current also. Just hold on, I will replace it. I am putting this initial direct battery only. अभी AC हम लोग बाद में करेंगे. So this battery of EMF E is put across the two inductance L1 and L2, and if I press the switch, current will start flowing here. So what I will see, the inductance EMF E will be equal to E1 plus E2 here, correct, and the same current I will be going in each of that. So further what I will say, E is equal to L times di by dt, this formula I also used. Here I would write L1 times di by dt, because in series current remains same, plus L2 times di by dt. This arrangement I can do. Now what can I see? This di by dt is common, hence I will say here that L is equal to L1 plus L2. This factor will happen. L is equal to L1 plus L2. So total inductance in series is adding as similar to resistors. So L1 plus L2, this arrangement will happen for inductance in series if there is no mutual inductance. There is no flux common to both. So this way we can write. Otherwise, mutual inductance is also taken into account, but geometrically they are placed such that they are not getting adding up. Correct. तो यह ध्यान देगा, तो inductance in series they will add up L1 plus L2 like this. Now again if I go for the parallel combination for inductors, that also I can write. Just see, it is one of the inductor, it is the second inductor, it is placed across a battery arrangement like this. See, now this battery of EMF E is coming here, it passing through the two inductors L1, L2. So current here will be I1, here current is I2 and total current is I. Now in parallel combination, what we know, the total current gets divided. I is equal to, this current is I say this current is I will write it as I is equal to I1 plus I2. This thing I can say. And EMF is same across each of that. Okay. I1 plus I2. Now EMF, whatever E is there, the same E will happen here and same E will also happen here. Correct. And we have the formula E is equal to L times di by dt. This formula I can write. Now, so for the current effect, I is equal to I1 plus I2, I will also say that di by dt, the term will be equal to di1 by dt plus di2 by dt. This is also correct. Okay. The rate of change of current will also go in the same factor. Hence, what can I say? Di by dt, I will write it as E by L, di1 by dt, this is E upon L1, di2 by d2, E upon L2. This expression I can write from here. Further, E is common, I will say 1 by L is equal to 1 by L1 plus 1 by L2. So, net inductance in parallel combination is following the same pattern as that of the resistors. No? So, this is for parallel combination. No? For parallel combination of inductors, the net EMF, how does it go? That also I have defined. Correct. This value, this thing we can see and apply it, we will get it done. Now, after this, for inductances in series and parallel combination, one more result I will say that what is the power and energy associated with inductor circuit. So, whenever there is for power and energy associated in inductor circuit, that also we can write. Say this is the inductor, I am putting here, this placed across a battery, this is the switch, and this battery of EMF E, inductance is L. If I press the switch, there will be the loop formation, closed loop, current flowing will be I, hence I will say E is equal to L times di by dt. This thing I can say, E is equal to L times di by dt. This is the voltage across the circuit. Na? E, the same voltage will be dropped here. Now, if I apply voltage with current E into I, so it will be L into I into di by dt. Now, you see E into I will be the power. Power is equal to what? L into I into di by dt. This is also correct for power in the circuit. Power, electrical power in the circuit. Now, if I go for P dt, power into time, this will be the work or energy here stored, and that will be, if I multiply this, integration of this Li into di. So, what I get here, the energy stored U is equal to Li into di, and if I integrate, so this term I will get it as half L I square. So, total energy stored here is half L I square in the inductor. In inductor, energy stored is half L I square. This thing we can use. This is important. How we get the energy stored and power. This was power. थोड़ा सा printing इसमें error आ रहा है. Again, I will write it as power. The power associated is this. Okay. Power and energy. For power, it was the equation. This thing I can apply. And energy also I have defined. ये आपका power की बात है. Okay. This for power and it is for energy. Half Li square. If you see, this term is quite similar to the electrostatic energy in the capacitor. And what it was? Half C into V square. The governing factor here, that there in capacitor was voltage, here it is the current, correct, and L is playing the same role as that of C. Okay, so power associated in the circuit also we can get, an energy also, that is half Li square. L is the self inductance. Now if I say this energy stored in the case of solenoid, in the case of solenoid, how I will get that also I am going to find. In the case of solenoid, if you see, this is the solenoid, say it is carrying the current I, number of turns are N and total length is L, area of the solenoid one loop is A, correct. I say the total energy stored here will be half L into I square, this thing I can write. Now for L of the solenoid we have done, half L is mu naught N square A into L into I square, this is U. The total magnetic energy stored with the solenoid, I can write it this, half mu naught N square A into L. This is the magnetic energy stored in the volume of solenoid, correct. This value we get. Now energy upon volume, if I say this energy U magnetic upon volume, if I have to write, what I will get? If you divide it with the volumes, I will say mu naught N square, and it is I square by 2. This term I am getting, na, because I am dividing the term with A into L. Further, what I will say, it is in a magnetic energy density. This I can say to be as magnetic energy density. This will be called as magnetic energy density, correct. This magnetic energy, if I write magnetic energy density, थोड़ा सा बोल्ड हो गया, कोई नहीं, थोड़ा ध्यान देना. So this value I write it as U small u b, and this value is mu naught N square I square by 2. Now see, in the case of solenoid, the magnetic field is B is equal to mu naught N into I. If I write this as B square by 2 mu naught, just see, is it the same? The B is mu naught N into I ka whole square by 2 mu naught. If you relate, so what you will get, just see, mu naught square N square I square by 2 mu naught. So if I put the value and solve, it is mu naught by 2 N square I square. It is perfect. So magnetic energy density UB, it is B square by 2 mu naught. This also we should keep in mind. The magnetic energy density for any inductor, this will be B square by 2 mu naught. It is quite important. This term magnetic energy density, ये आप ध्यान देंगे, magnetic energy density, and this is what, B square by 2 mu naught. If you remember the electrostatic energy density, if you remember there, electrostatic energy density, that it was half epsilon into E square. It was the electrostatic energy density. Electrostatic energy density. Energy density. That was half epsilon E square. And here I am getting B square by 2 mu naught. It's quite important formula, and it is used for finding out the magnetic energy density. And even if you know the magnetic energy density, we can easily find out the total energy associated with the arrangement. All these terms we can see, और इसका रिजल्ट हम लोग बना सकते हैं. In certain cases, I will relate it also. The magnetic energy density along with the in the solenoid, how does it go? Correct. So if I am going for this magnetic energy density, how you will see, say I am taking for solenoid. In the case of solenoid, if I say the length is L, area of cross section is A, number of turns per unit length is n. N is the number of turns per unit length. Suppose it like this. I said that kinetic energy density UB, it is B square by 2 mu naught. Now if I multiply with the volume of solenoid, it is A into L, area of cross section into total length. If I multiply this A into L, so this will be the total energy. U magnetic arrangement I can write. Now if I put the values, what I get, mu naught N into I का whole square by 2 mu naught into A into L, that is U magnetic. Now you see here what I said, that it is mu naught square N square I square A into L by 2 mu naught. And if I put it as half L into I square, so this will go quite correct, na? This will go quite correct, because if I see coefficient of current, here it is I square. If I remove this factor of I square here and I square here, what I will say, just see, half L, it is what? This value. If I say, the term will be mu naught N square A into L, correct, into half if I do, na? So that will show the kinetic energy. Half L, if I am putting half L into I square, so this is the inductance L. You can very well see half Li square arrangement is the same value, meaning that I say kinetic energy density into volume, that is half L I square. So this formula is quite frequently used for finding the kinetic energy. So these are the two methods for finding inductance. Inductance को यहाँ से भी we can relate that the total energy U is equal to half L I square. So I will say 2 U by I square also will be the formula for inductance. Another inductance formula is this also, 2 U by I square. This will also give the value for inductance. So this result is also defined, correct? Inductors in the series and parallel combination, फिर energy density, all that I have defined, correct? Now, there is also a case of mutual inductance, what it is. Next I will go for this case of mutual inductance. How we see this? Na? The mutual inductance will do. Next is this mutual inductance. Let us see how does it work. Mutual inductance means if there is a current change or flux change in the first coil, there is always induced EMF or current in the second coil. So production of induced current and EMF in the second coil due to flux change in the first coil is called mutual inductance. इसका हम बेस्ट ऐसे एग्जाम्पल ले सकते हैं कि अगर किसी पड़ोस में कोई अच्छी घटना दुर्घटना हुई तो आपके ऊपर इसका इम्पैक्ट आता है, तो बगल वाले के हिसाब से आपके सर्किट में क्या चेंज आ गया, जो डायरेक्ट इम्पैक्ट चेंज आता है, दैट इज डिफाइंड एज म्यूचुअल इंडक्टेंस. एंड वेन एवर आई हैव टू डिफाइन द फ्लक्स phi remains same, phi is equal to, I will say that phi 2. If I say the flux is the second coil, mutual inductance M, the current will be of the first coil. This formula we can keep, and it is also equal to, if I say here phi 1, if I say flux in the first coil, M current in the second one, means if we are finding the flux in second coil, current will be the first coil. If we are finding the flux in the first coil, current will be of the second coil. And from here again, if I say the mutual inductance M, that is phi 2 by I1, or it is equally true for phi 1 by I2. Mutual inductance of first with second or second with first, the value remains same. It doesn't change. Meaning that, how does it go? I will take it. Just see how it is. Suppose I say this is solenoid arrangement and it is having the length L1, area A1, number of turns is N1. L1 length is like this. Correct. I am making the current flow here I1. ये आपके पास है. Now in the vicinity of this, say it was flowing and this coil was attached to a battery and there is a switch arrangement here happening. Correct. So current flowing here was I1. Now if I attach a second solenoid arrangement like this, this is the second solenoid. The second solenoid is like this. Just see. In the second solenoid, there can be, in the second solenoid, there will be the induced current and EMF. Some induced current and EMF can happen if I attach to a galvanometer. If I attach to a galvanometer, so there can be the second, in this coil, second solenoid, there will be induced current. So that induced current in the second coil and EMF, we can get the flux associated and mutual inductance. So this I will do in the next page, how the flux is associated with the second coil due to current change in the first. ये थोड़ा यहाँ पे overlap कर रहा है, तो इसको I will do it in the next page. Just see what I am doing. The first coil solenoid is this. It is attached to a battery. This is a switch arrangement here. Correct. And in the vicinity of this, I'll put a second one. And there is only galvanometer and no battery. Here is this battery E. If I press the switch, current I1 is flowing. In this coil, first one, number of turns was N1, area A1, length L1. Second coil, number of turns is N2, area A2, and length is L2. You see, with the second coil, area is A2. Second coil area is A2. Okay. And the length here is L2. L2 is the length, area is this. And I say this L1 length, if you see, I can say this L1 length is more than L2. But area A2 is more than area A1. Now I am making the current flow I1 in the first solenoid. So, magnetic flux phi 2 I have to see. The field will be due to first coil because here the battery, here the current. Field is B1 due to first coil. What is common with the second, you will see. And the field is this, then area common. If you see, area common for which flux will be associated for A1 and A2, area common will be of that of A1 only. A1 only, no? A1 area. But number of turns I will take for the second coil because flux I am watching with the second coil. It is N2. And length also has to be common. Common length of L1 and L2 will be L2 only because L2 is less than L1. So it is L2. Now put the values. B1 is mu naught N1 I1 into A1 N2 L2. It is phi 2. So what I get? Mu naught N1 N2 and it is your A1 and L2. Coefficient I1, it is phi 2. From here I will say phi 2 by I1. Phi 2 by I1, if I say it is mu naught N1 N2 A1 L2. Correct. So this is the mutual inductance. So mutual inductance, what I got for the two solenoid, it is mu naught N1 N2 A1 L2. This term I get. Meaning that with the second self inductance, that N square is being replaced with N1 into N2. Rest of the parameters are remaining same. The flux with the second coil for the current flow in the first coil we got this idea of mutual inductance. And if I reverse the pattern, meaning that if I see phi 1 over I2, this value of mutual inductance will again remain same, and this will be again mu naught N1 N2 A1 L2. This you will get. Either we find for the flux with the second coil or first coil, mutual inductance is same and its unit is also same. That unit of mutual inductance is again called Henry. So anyway, the factors they can be related. Matlab what I am saying, this mutual inductance M, this phi 2 by I1 if you see, or phi 1 by I2, result are same for mutual inductance. So these parameters are important for finding the flux and mutual inductance, self inductance, everything I have defined, correct? This thing for self inductance, mutual inductance, energy, power, energy density and all I have defined, correct? So this value it can be used. Now with the flux chain and all, I will also see the time varying current in RL circuit. This concept also we can see. What is the time varying current in RL circuit? How it is defined also we can do. Meaning that if I have a inductor, it is attached with the resistor, it is connected to a battery and there is a switch. Arrangement is like this way. This battery of EMF E, inductance L and resistance R. Correct. If I press the switch here, the current starts flowing in the circuit. If I press the switch, current starts flowing in the circuit I. Now see the voltage develop across the inductor, it is E1, across the resistor it is E2. Polarity it is always oppose the thing, that is plus minus, because the local battery inside the inductor will always oppose the flux chain, it will oppose the incoming current. Here also it is plus minus, and I can apply this loop rule. I will say that E minus E1 minus E2, this term will be 0. No? So net EMF of the battery will go like this. Now if I put the results, what I will say? E minus E1 due to inductance L di by dt minus I into R, this value is 0. Correct? Current flowing is I here. Now what I will say? E minus I into R, it is L into di by dt. This thing also we can write. Further what I will say? It is di over E minus IR. Just see di over E minus IR. It is dt upon L. I can integrate both left hand side, right hand side by separation of variables of same type, the di over E minus IR, and it is dt by L. If I integrate this function, so what I will get? Just see di over E minus IR, this value will be integrated as ln E minus IR, na log function dx over 1 minus 2x type, and the coefficient is r minus 1 by r, it will come out, and this is equal to t by L. This result we can put. So further here, what I will say in this arrangement, if I see, I will say that ln E minus IR value will be equal to minus R by L into T. This factor we have. Just see what the result I have done. For EMF current, the expression is E minus IR is minus R by L into T. This thing we can define. Correct? ln E minus IR minus R by L into T. From here I will getting it. Now I will put the conditions what they are. At T is equal to 0, no current will flowing. After certain time some current is there. So this formula I will put it in the next page. Just see what I will say. ln E minus IR is equal to minus R by L into T. This expression we have. Now we'll put the condition for T is equal to 0. Current flow in the circuit, here I will say that if the condition is here, the current flow in the circuit is 0. For any time T, current is I. If I put the result like this, just see the mathematical equation, ln E minus IR minus ln E is equal to minus R by L into T. Log A minus log B, log A upon B, ln E minus IR over E, this value is minus R by L into T. Further, if I solve, I will say that E minus IR over E, this value is minus e to the power minus R by L into T. This expression is also correct. E minus IR is equal to E into e to the power minus R by L into T. This term we have. Till now, what I have derived, it is like this. So further I will say, if I put the value for current IR, what the value of IR? It is E times E minus e to the power minus R by L into T. Further I will say this value is as I into R is equal to what? It is E times 1 minus e to the power minus R by L into T. This factor I will write. I am saying that it is I into R is equal to E times 1 minus e to the power minus R by L into T. This thing we have. So current in the circuit here will be I is equal to E upon R times 1 minus e to the power minus R by L into T. The exponential function will get for the current flow here. Just see the exponential function. The current is varying with time and the question is this. E is equal to E by R 1 minus R by L to the power T, e to the power this. Now for this condition, if I say for T is equal to 0, you will find that current in the circuit is 0 because e to the power 0 is 1. And for T is equal to infinity, that is called steady state, e to the power minus infinity is 0, the current is E by R and that is the maximum current flow in the circuit. So this current is varying from 0 to E by R and is following the exponential function. So this result we can draw on the graph also. What the current is flowing in the circuit and these conditions we can put and draw it. A maximum current is this. So in the next page I will see this thing. Current value I am saying here is as I is equal to E by R times 1 minus e to the power minus R by L into T. This thing we have. Now if I have to draw the graph, just see, if I have to draw the graph for this function, for T0 current is 0, I versus T, I can draw the graph. So this graph will go like this. Later onwards, T large values, this is going for the maximum current here, that will be maximum current I max will be E by R in the circuit. Means maximum current is E by R. Matlab at that point, resistance offered by inductor is 0. Resistance offered by inductor is 0 at last time. From this equation I say resistance of inductor is 0 at T is equal to infinity or steady state. And initial current, you see initial current was 0. So resistance of inductor is infinite at T is equal to 0 because their current was 0 at T is equal to 0. Meaning here I can say that inductor resistance is changing with time. Now that is also some exponential factor we can get. And here this term R by L, just see, I will say that this current expression I is equal to E by R times 1 minus e to the power minus T by tau. Tau is called time constant of the circuit tau and this tau is L by R. It is called as time constant here in the circuit. It is the time constant, and that is always remaining constant ratio of L by R. If you compare with the RC circuit also there, what we got RC, R into C was the time constant, and here it is L by R, that is the time constant. And also we can say at T is equal to 1 tau is equal to L by R. If I put, so current value will be, just see, E by R times 1 minus e to the power minus 1. So at this time, what I get the value of current? It is E by R times 1 minus 1 upon E. Further, if I solve, it is E by R times E minus 1 upon E. Value of E, 2.72 approximately. So current after one time constant, that value is maximum current times E minus 1 to 1.72 over 2.72, and this result is approximately 0.63 of I naught maximum current, or 0.63 of E by R. In one time constant, this current reaches 63% of its maximum value. Also we can see, this time is tau, T is equal to tau, for which the current here 0.63 of E by R. Now, the maximum current reaches the 63% of its maximum value. And later onwards also we have this term. So time constant is also there. And this time constant also defines one thing, that if initial slope is remaining constant, in one time constant, current reaches the maximum value, had the initial slope been remaining constant. But for this exponential graph, slope is decreasing with time increase. Continuously there is a decrease of slope, that's why it takes the infinite time. Had the initial slope been constant, in one time constant, current would have reached the maximum value. So for the current flow in the circuit, this equation we see. And also we are defining the resistance of inductor is varying with time. So inductor blocks the current at t is equal to 0, and inductor fully supports, act as a pure conductor with time tending to the steady state. So resistance of inductor varies with time. I can say that resistance of inductor decreases with the increase in time. This value we can see. Here result approach we can make. Always it will be helpful. And at any time, if we have to find the energy or power, that always we can get. Correct? Energy and power in the circuit also we can get. Here I have defined this. Also I can say the inductor and it is the resistor, they are attached in the circuit. This is a DC battery with a switch here. What can I say? This is the inductor, this is the resistor, current flowing was I. So if I say the power by battery will be also equal to power in inductor plus power in resistor. It is also always correct. Power by battery is equal to power in inductor plus power in resistor. Anytime this always be correct. This thing we can see, or I can say rate of change of power supply by battery is equal to rate of change of energy in inductor plus rate of change of energy in resistor. This will always be correct. Okay, this thing will happen. And current flow in the circuit we have seen. Also I can find out the voltage across inductor. At any time if you have to see, I can see it is equal to L times di by dt, and this will be also equal to E minus IR at that time. So both will define the this is the voltage. This is the voltage across inductor. The voltage across inductor is this. This will always be correct. Voltage across inductor L di by dt, it is also equal to E minus IR. Now this thing we can see. Sometime here the condition is asked the maximum rate of power on inductor. If I have to see maximum rate of power on inductor, how do we get? For maximum rate of power on the inductor, this will happen when resistance of inductor becomes R, and this happens when the current I will be equal to E and both the resistance are equal, so it is 2R. Correct. So this value is the current. And in this case, the power maximum, if I see the same case of resistors, E by 2R squared into R. So this power maximum, if I see the similar case we have done for the case of RC circuit, it is E square upon 4R, meaning that the maximum power is generated in the circuit when load resistance and inductor resistance are equal, and this I can derive with the help of maximum minima conditions. If I derive the power supply in the circuit and differentiate and make it equal to 0, always we get the result. Always you should keep in mind the power dollar in the circuit, how do we get, and current flow supply, here it is. Okay. So this was for time varying current and voltage in the circuit. Even we can see the decay of current in the circuit also follow the same result, decay of current in circuit. It will also follow the same rule. Okay. Energy stored in inductor and it changes to the resistor and all. No. So decay of current, if I see the I, this is E by R times e raised power minus R by L into T. This value we can put. The current in the circuit also decreases same way as that of RC circuit. So this result will also happen either for the change of current, increase of current or decrease in the current in the circuit, RL circuit, all we can see. And heat produced, if I have to see, just see what was the energy, and if I see the heat produced during the decay, it will be I square R dt का integration, and if I compare it go from 0 to infinity, you will get it equal to half L I square, meaning that if you put all the values here, E square by R square e to power minus 2 R by L into dt integrated and relate it, it will always come out to be half L I square, meaning all the energy stored in inductor converted into heat. So this formula is there when any fully charged inductor is connected to the resistor. It is the inductor and it is resistor. All the energy stored in inductor converts into resistor. So this formula for decay of current in the circuit, this is the inductor and it is resistor. All the energy stored in inductor converts into resistor, and that half L I square is I square R dt, heat produced is energy stored. Similar to that we have done in the capacitors, I square R dt was equal to half CV square. All these conditions they can be found and we can get it correct. So this was for inductor, inductance, energy stored and everything I have discussed. Some basic more questions we will do in the next class. Thank you.